Wait, so we're doing this project on prime numbers, right?
Yeah.
Is 1 considered a prime number? I think it is, right?
1 is definitely not a prime number.
Why wouldn't it be
Because a prime number is anything that can be divisible by 1 in itself.
I'm going to look it up because you're wrong.
No. I'm right.
Okay, a prime number is a natural number greater than 1, so 1's not a prime number.
Definitely
You're
not.
right.
These are all examples of prime numbers. The first few prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. A prime number is a whole number greater than 1, whose only two whole number factors are 1 and itself. Next, we have a composite number, a whole number that can be divided evenly by numbers other than 1 or itself, pretty much the opposite of a prime number.
To prove that there are indeed an infinite amount of primes, first we're going to prove that there aren't a finite amount of primes. This is what's known as a proof by contradiction. First, we have to make a list of all known primes. This is a finite list. This is a complete list of all the possible prime values. This list is prime 1, prime 2, prime 3, prime 4, all the way to prime n, where prime n is the last prime. If there is a prime not on the list, then this isn't a complete list, and that number needs to be added to this list. Now, we're going to multiply all the primes in our complete list of primes. We're going to call this p. P is equal to prime 1 times prime 2 times prime 3 times prime 4, all the way up to times prime n. P is the product of all numbers in our complete list of primes multiplied together. Now we're going to make a new number. It's going to be q. Q is equal to the product of all our primes multiplied plus 1. P can be divided evenly by our prime factors, but q is going to be unable to be divided evenly. In many cases, this is going to result in a prime number. Q is going to equal a prime number, and this is going to be a prime number that is bigger than our list and is not on our list, meaning that this is going to be a new prime number.
Now for an example of this, we're going to start with our complete list of primes. 2 and 3. These are the only primes in the world, the only primes that exist. We're going to multiply our list of primes. 2 times 3, which is equal to 6. And then we're going to add 1 to it, and we get 7, which is a prime number. Well, we messed up. 2 and 3 aren't the only primes in the world. Now we have 3 primes, 2, 3, and 7. That's our complete list of primes. That's our new complete list. We're going to multiply them together. 2 times 3 times 7, which is equal to 42. Now we're going to add 1 to this and get 43. 43 is also a prime number, so our list was wrong again. Now our list is 2, 3, 7, and 43. We're going to multiply our primes again. 2 times 3 times 7 times 43, which is going to be equal to 1,806. Now we're going to add 1 to this, and we're going to get 1,807. Now, this is actually not a prime number. It is, its prime factors of it are 13 and 139. So our list wasn't complete. We missed a few primes along the way. Now our list is 2, 3, 7, 13, 43, and 139. Now we're going to multiply these again. 2 times 3 times 7 times 13 times 43 times 139. this is going to be 3,263,442. Now we're going to add 1 to this. We're going to get 3,263,443, which is a prime number. Now we add that to our list, and this series continues on infinitely because there are an infinite amount of primes. There is no end to this list. This list will keep on getting bigger. Every prime number that we get by adding 1 to the number before it, the number that is the product of all the numbers in our list, every time that product plus 1 is a prime number, we add it to our list. Every time it is a composite number, we take its prime factors and add those to our list, and that just continues on infinitely.